Hi, welcome to the seventh and final section of this course. In this section, we will develop a functional style exercise. This section is divided into two videos. In the first video, we will consider the application of two-dimensional collision detection, and we will consider a stream implementation of this kind of algorithm. In the second video, we'll consider more advanced algorithms for the same problem. These algorithms are based on the notion of spatial grouping of objects. Now let's start with the first video of this section on 2D collision detection. In this video, we will learn the basics of collision detection. So we will learn about bounding shapes and bounding boxes, and about the basic two-dimensional collision detection algorithm. Then we're going to consider a way to use streams to obtain a parallel implementation of this algorithm. And based on this implementation, we will perform some tests. So, as our application, imagine a two-dimensional game. In a typical two-dimensional game, we have some game objects which move on the screen and may possibly collide or overlap. And usually, some of these collisions, at least some of them, are relevant to the game because they give rise to game events. Therefore, the game needs a way to efficiently detect collisions, especially if it manages many different game objects at once. Now, usually game objects in these kinds of games will be depicted as sprites. A sprite is nothing else than a bitmap image that can move on screen. And sprites may have arbitrary contours, such as this bunny character here on the right-hand side. Therefore, if you try to do exact collision detection between arbitrary sprites, this is going to be too time-consuming. So what real games do is to replace sprites with simpler bounding shapes. So on screen you will see the actual sprites, but behind the scenes the collision detection is going to be performed with simpler shapes. And the two simplest shapes you can use for this purpose are a circle, so you can have a bounding circle around your sprite, or a box, more precisely an axis-aligned bounding box, which is just a box that is parallel to the axis of your screen. And in our example, we will use this second idea. We will use axis-aligned bounding boxes. Now let's switch to the code. We will use the following 5 classes. There's box, representing a bounding box. We have collision, which is the object representing a collision between two boxes. We have basic detection with the basic algorithms, and one of these algorithms uses a custom collector called for each collision collector. And finally, our main method, so our entry point, will be in the counting test file. Now let's switch to the code. Okay, let's start with the box class. So this represents a two-dimensional box on your screen, and for simplicity and for performance, I'm just avoiding encapsulation. I'm just exposing these 4 integers which represent the coordinates of the 2 corners of this box. And this is not as odd as it may seem. It's actually done in several real-world cases, such as in the Android API, you can find a very similar class called android.graphics.rect. And besides these 4 integers, this class has a very plain constructor. Then there's a static method called rOverlapping, which takes 2 boxes and checks whether they are colliding or not. Finally, it's handy to have a static method called newRandom, which returns a new random box with this maximum coordinates and this maximum width and a certain maximum height. We're going to use this method over and over again in our tests to start with a random collection of boxes. Next, we have the collision class. So a collision is just a pair of boxes. The only special feature it has is that the order of these two boxes is not relevant, because a collision between A and B is equivalent for us to a collision between B and A. And we obtain this irrelevance of order by overriding the standard hash code and equals methods in the appropriate way. Now let's take a look at our collision detection algorithms. So for these first tests, we choose the following API. We're going to test functions, such as this one, that accept a collection of boxes and a consumer of collisions. We can also call this object a collision handler. And the objective of these functions is to execute the handler on each collision arising from this set of boxes, from the given set of boxes. Our first algorithm is extremely simple. It iterates twice over the collection, so in such a way that it's actually iterating over all pairs of boxes in the collection, and it checks whether this pair of boxes is colliding, and if these two boxes are colliding, it will pass to the collision handler a new collision object containing these two boxes. So very simple. The only problem with this algorithm is that it's going to execute the handler twice over each collision, because each collision will be encountered twice. The first time as the AB collision and the second time as the BA collision. So even if we said that those two collisions are equivalent to us, if we use this very simple algorithm, each collision is going to be visited twice. So to solve this problem, we have this second version, same signature, but we only consider ordered pairs of boxes AB, with A coming before B in the list. So which list? Well, our collection of boxes now becomes an array list, because to implement this algorithm, we need to switch to so-called positional access to the collection. So we want to use explicit integer indices in such a way that we only consider each pair of objects once. And the trick is the following. We have an outer iteration from 0 to the length of the list, and we have an inner iteration which starts right after the position of the current outer loop. And unfortunately, you cannot do this with standard iterators, so you have to switch to explicit integer indices. And then what we do for every pair is just the same thing we did before. We check whether they're overlapping, and if they are, we call the collision handler. And finally, let's do it in a more interesting way, using a stream, and in particular using a parallel stream. So same signature, a collection of boxes, and a collision handler. We turn the collection into a parallel stream, and we collect this stream right away with a very special collector called the for each collision collector. So as you can see, the constructor of this collector accepts the handler, and then it provides these two methods, update and merge. So let's take a look at this collector class. Here it is. So this collector has two fields. The first is the handler that is going to be called for each collision. And the second field is a list of all previously seen boxes. We call this the cache of this collector. Now let me point out that in some sense it's quite unnecessary to store these boxes again, since they are already stored in our original collection. However, it's the way that streams work. So since we decided to use streams, and we decided for a very good reason, and the reason is that they help us parallelize our code. However, In this case, they have the following drawback. The string is going to provide one box at a time, but our collision detection algorithm does not work on a single box at a time. It's quite the opposite. To check for collisions, you have to compare the current box with all previously seen boxes. And that's why this collector unfortunately needs to store all previously seen boxes, even though those boxes are also already stored in an outside collection. Now, the constructor of this class is very basic. It just stores the handler. Next, we have the update function, the update method, which processes a new box. So what does it do? Well, for every previously seen box, let's call it A, it checks whether this old box A overlaps with the new box B. And if it does, we call the handler. And then finally, we store the new box in our cache. That's it. Next, the second method, recall, as we saw in a previous video, this merge, also known as combine method, is needed to have a working parallel collection operation. So the task of this merge method is to merge another collector of the same type with this one. So it receives another collection of the same type called other, and merging these two consists in merging their caches that we do here as the last line, but also in calling the handler on any cross collision. So on every collision that occurs between a box that was seen by this collector and a box which was seen or processed by the other collector. So we iterate over all boxes from the first cache and all boxes from the second cache, and if these two are overlapping, we have to call the handler on them. That's all we need, so we can switch to our main method and our actual test. Well, in this class, we fix some imaginary resolution, which corresponds to the standard full HD resolution. We also fix the maximum size of a box to 200 pixels. Then it's handy to have a method which builds a list of n random boxes. And finally, we come to our main method. For these tests, we are testing over a random array list of 5,000 boxes. And on this collection of 5,000 boxes, we are running our 3 versions of the for each collision method. So here we have the for each collision 1, version 1, then we have version 2 and version 3. And version 3 is the one based on a parallel stream. Now, all of them execute some action, which is a consumer of collisions, and in our case, we do something very simple, which is just count the number of collisions. And to do this, as you can see here, we define a consumer of collisions that takes a collision, ignores the collision itself, it just increments an atomic counter, which is this object of type long adder, which can be incremented by different threads at the same time with no race condition. So it's suitable to be incremented in parallel by different threads. And here are our 3 tests. If you're new to Java benchmarking, let me point out that this is a very basic way of measuring performance. I could have used more specific so-called benchmarking harnessing tools, but for our purposes, this way is precise enough to show the difference between these implementations. And you should know that every time I run one of these algorithms, I run it twice, first as a warm-up, and the second time I actually time it with the help of this time class. And the reason why I run every test twice is that in this way, you give the Java virtual machine the opportunity to compile and optimize the performance critical part of your tests. And this is very standard procedure with Java benchmarking. Okay, I think we are ready to check the performance of these algorithms. This is a typical output. So the standard imperative version that counts each collision twice, in this case, it took about 200 milliseconds for starting from 5,000 objects and counted about 400,000 collisions. However, this is actually twice the number of real collisions. So if we switch to the second imperative version, the one that considers each pair only once, it takes less than half the time of the first one, and it measures half as many collisions as the first one. Finally, the third version, which is based on a parallel stream and on our custom collector, takes somewhat less time, about, in this case, 30% less than the second one, and obviously counts the same number of collisions. That's all for this video. So we learned that streams ease the path to parallelization because it was relatively easy to obtain a parallel version of our algorithm. We just had to turn our algorithm into a suitable custom collector. And we had to do that because we're dealing here in this exercise with a naturally stateful algorithm.